Apology materials or another workshop coordinator, Professor Marcus Alden from Lund University. Briefly, I introduce Marcus. Marcus was born in 1954 in Vargarda in Swiss part of Sweden. He got his MS in engineering physics in 1978 at Chalmers University and Technology in Gothenburg, and his PhD in physics at Lund University in 1983. The thesis entitled Application of Laser Techniques for Combustion Studies. Professor Alden has, among other scientists, committee been chairman of the Gordon Conference on Laser Diagnostics of Combustion in 2003 and served the program for chair of 31st International Symposium on Combustion in Heidelberg 2006. He is the professor in physics department at Lund University from 1992, and also as a guest professor in some other universities. Alden has a co-author of 395 regular papers with reference system and 386 conference contributions. Most of them in the field of laser optical diagnostics of combustion and high temperature system cooling and H index of 52. We thanks Alden to accept the invitation for this to be presented throughout this workshop. We have two sessions. In the first session was 1 hour and a half, and after a break we have the next session. Thank you.
Thank you. Thank you. I'm sorry, going back. Thanks for the introduction. It's really a pleasure to be here. I've been overwhelmed by the hospitality of the Iranian people. Thanks a lot for taking me around and showing the city and taking me to different places. I put together a program in this workshop. I will come back to the schedule a little bit later. I could say that it's based on a series of lectures that I've had at different places. It's summer schools in Princeton and Tsinghua, and also in China, where I teach a course every year. So just before I go into the program, I could give you a little bit view on where I come from. I'm not quite sure you know so much about Europe. Here you can see Sweden, here is Denmark, and here in the very south is Lund. And you can see with that we are very close to Copenhagen. This is Malmö, this is Lund. So it's very convenient to fly around because the train from Lund now with the new bridge, well new, it was built in 2001, it takes only 30 minutes to reach Copenhagen. So it's very convenient. Just a couple of words about Lund. It's a pretty old city. It was founded in the late 10th century. And Lund was actually belonged to Denmark until the mid-1600. Then it was a lot of wars between Sweden and Denmark. And finally Sweden was beating Denmark and took sort of this part so that now it belongs to Sweden. You can see still a lot of signs from Denmark in Lund. So it became Swedish in 1658. So now we are on the order of 110 students, half are students. So it's 110 inhabitants and half of them are students. So it's heavily dominated by students. Just very briefly about the university. It's what we call full university with a lot of different faculties. We have a medical faculty, philosophic faculty, science faculty, and an engineering faculty. And in the engineering faculty, which is also called Lund Institute of Technology, we have 18 departments, mathematics, chemistry, mechanical engineering, and so on. And in one we have Department of Physics. And in the Department of Physics we have 9 divisions: solid state physics, atomic physics, nuclear physics, and one which is Division of Combustion Physics. That was created in 1991. Actually, it was a split off from atomic physics. So my background is in atomic physics. But then in 1991, it was seen as we have sort of outgrown the division of atomic physics. So we created a new division, and the main research areas has been, still is, combustion diagnostics, and we also have an activity in chemical kinetics. And here are a little bit of our funding. We have an approximate budget on the order of 4.5 million euro per year. And we are roughly 60 people, some courses, the personnel. We have around 30 PhD students now, 2 from Iran, doing very well, several from China, Russia, and I think that is really very interesting to have a lot of students coming from different cultures, and that where we can learn from each other. And since we were created, we have had 75 PhD theses, actually one coming up tomorrow in the area of spray diagnostics. Okay, so that was just a short introduction, general. And when I was asked to give a workshop, I wasn't quite sure exactly what to include from the sort of 16 lectures, full lectures that I've had before. But I will try to have one pass on introduction to this, a little bit of definitions compared to other diagnostic techniques. And then I'm not quite sure what background you have here. Do you come from mechanical engineering, chemical engineering? Yeah. So I know from previous lectures that this might be a little bit hard. I mean, but this is very important for the technique that I'm going to describe. It's based on spectroscopy, meaning that we actually probe molecules and atoms. And in order to do that, you have to have a certain knowledge about what is an atom, what is a molecule, why do we have energy level diagrams, why are we able to measure temperature. So this will be a very stripped version of this. So there you might, if you don't have a sort of this background, you might think that this is a little bit too much, but this is still very important. Then I will also continue with a little bit on instrumentation. What is a laser? What kind of equipment do we need in order to do the experiments? And then I will focus on various techniques. Laser-induced fluorescence, that's the main technique, and there I could actually talk the whole time. But I will concentrate on the application on laser-induced fluorescence. Very, very briefly about the theory, the background, and the underlying physics. So that will be very short on the background, but then trying to describe how can these techniques be used in engines, gas turbines, and furnaces. And then it will be pass on Rayleigh and Raman scattering. Also there, pretty brief on the theory, focusing on the potential, limitation, and possibilities. And then I'm not quite sure where in time I am. So maybe I will have time also to describe coherent anti-Stokes Raman scattering cars, and also there focusing on the application, and also maybe eventually a little bit on soot diagnostics. And I'm not quite sure how you used to do with questions. I have no problems. If you have any questions, just interrupt me. Rather than maybe take all the questions at the end. But it's up to you. I encourage questions. There are no silly questions, maybe just silly answers. But I mean, it's very important that you really say if you don't understand or if you want to have any questions. So, by that, combustion diagnostics, what is that? Well, this is kind of my definition on how the techniques can be divided. I used to divide them into probe techniques, where we can have, for example, gas chromatography, thermocouples, hot wire, mass spectrometry. I have no expertise in this, but I just very briefly mentioned about the limitations. And then you have the other technique, which is based on optical methods, generally using optics. And then when you can divide this further, you can have what is called non-spectroscopic technique. That means that you really don't care what kind of color you have on your laser or optical source. So here you can have Schlieren shadowgraphy, you can have interference holographic techniques, you can have LDV, PIV, LDA, and so on. I will also very briefly touch about this. I really don't have any deep background in that. But then we go over to the spectroscopic technique, which is based on that we can change the color. You know, this color is green. It's very green. It has a certain wavelength, which has a limited application in diagnostics, because it's just an accident if we can hit a molecule which has an absorption at this wavelength. So here we are looking at various techniques as well. We can look at natural emission. You know that a flame emits light. That, of course, can be used. Now I will mention about this. And then here you don't have any laser. Then you have more in the laser spectroscopic technique, and you can, of course, do absorption, but that is not necessarily that you need a laser. So I will also very briefly mention about this. But then you have this division into incoherent and coherent techniques, which I will define later, essentially based on linear optics or nonlinear optics. So essentially the workshop and my background is in this field. So that will be what I would talk about. A little bit on history. I've been lucky enough. I started to do my diploma work in this field in 1976. And at that time, there were some papers that came, I would say, in 72, 73. And at that time, the focus was on Raman Rayleigh scattering, simply because at that time, most of the lasers did only have one wavelength. So it was not that easy to scan the wavelength. And in these cases, you don't have to scan the wavelength of the laser. To my knowledge, the first conference in this field was held in Schenectady in US. It's the headquarters of General Electric, which in the 70s was sort of the place where they had most activities. And I had the opportunity to spend 8 months, roughly, in Schenectady working with these people in 78, 79. Then, in the early 80s, you could see the first real application that came in engine application, in gas turbine. LIF started to be developed because here you really need a tunable laser, which was not the case here. And then in the 90s and further on, various advanced techniques based on to a large degree on multidimensional visualization, and also different nonlinear techniques. And what we see right now are a lot of combination of techniques put together to visualize combustion processes, and also really to try to quantify the results even in real-world application. And with real-world, I mean big burners or furnaces or gas turbines. And that is, I would say, where we are right now. Here are some background material. Sort of the Bible has been for a long time. It's pretty old right now, but that has been Alan Eckbrett. Wrote a thorough book on laser diagnostics for combustion. The second edition was published in 1996, so there you have a lot of background materials, a lot of physics. Then Katarina Kors and Jay Jeffries had a book with a lot of contributions in 2002. And then there has been 2 overview presentations at the Combustion Institute. Katarina presented, and we were a lot of co-authors that presented an overview in the 2005, and I had an invited lecture in 2011. So these are sort of review articles in the field of laser diagnostics, which you can go to see the state of the art. I mentioned in my lecture the other day that for me this field is actually divided into 3 different fields. In the first area, there we really have to try to understand the physics. What happens when a laser beam interacts with a molecule? It's not quite clear. I mean, it could be high pressure, it could be a lot of strange things going on. The line shape changes when you go to higher pressure. And these are things that you really have to investigate. For example, how would a spectra look like at 30 bar and 3000 Kelvin? This is nothing that you necessarily could find in a textbook. So you really have to do a lot of basic work, which might seem as just a waste of time. But still, this is where you put the foundation for knowing the accuracy and the precision of the various techniques. And it's also here where we sort of develop new techniques. We collaborate quite a bit with industry, and often they come up with, can you measure that? Can you do that? And most often we say that I'm not quite sure, but we can try. So this is the area where we sort of still, I would say, are physicists, trying to understand the interaction of light and matter and also develop completely new techniques. But this wouldn't be sufficient. We are right now in a division on the order of 60 people. Sweden is a small country. If we would do only this, we would be a group of maybe 3-4 people. So that would not be sufficient, even if it would have been top-notch in the world. I mean, that's not sufficient to have 60 people working on this kind of basic research. So it's also very important to apply this together with colleagues. Most of the people in my division comes from physics, come from sort of the diagnostic area. And many and most of us do not really we are not really combustion expert. So in order to face the real combustion problems, we have to have close collaboration with experts in the field of heat transfer, in the field of CFD, in the field of kinetics, and so on. And here in this area, we really want to apply the work that has been developed and then apply it in well-defined flames, turbulent flame, laminar flames, to produce data of as high quality as possible to measure important parameters, temperatures, velocities, concentrations. So this is for model validation. And then finally, and also very important, that is to really bring all these techniques out in industry. So most of our lasers, at least many of them, are on wheels, meaning that we literally take them into a truck and move them to the industrial site. That could be Siemens in Finspång, it could be, which is 400 kilometers away. It could be to Scania, which is 600 kilometers away. It could be to Volvo in Göteborg. Or boilers belonging to power producing companies. And all of this constitute the activities. It's not that these are divided. I mean, we don't have people only working in this. We have people mainly working in this, but then they also participate. And I think for our credibility, it's extremely important not to fool sort of our customers, our industry, to say that, well, we can measure that, and then to make a demonstration, and then don't do anything more. It's extremely important, if we have an idea, not only to show it in the lab. I forced a lot of my colleagues to also demonstrate in engines or gas turbines. It doesn't always work, but it has to do with credibility. You can't say that you want to do this because it's of importance of engines. Then demonstrate the technique in the lab and then go on to a next technique. Then you will lose confidence with your industrial partner. So that's why some of the techniques that are developed here have turned out to be useless in the application. But that's science, right? You don't know which of these techniques will end up here. But at least we have to try. We have to prove that it doesn't work. So all of this is sort of all these activities is very important. And in our division, one day we could have a visitor from, well, a Nobel Prize winner coming to visit us. Next day we could have a CEO from a company. And I think this has been very fruitful. And that's why we have been able to have on the order of 60 people working with more or less pure diagnostics. And I can also say that nowadays we have not only activities in combustion, we try to develop this technique for other applications. For example, in plasma diagnostics, gasification, catalysis, production of nanowires for new sun cells, where we have a lot of high temperature phenomena going on. So these techniques that has been developed for combustion could equally well be used for trying to understand plasma process. Okay, so very briefly on the probe techniques, where I, as I said before, really don't have any background. Some of these techniques for a thermocouple, I think you agree that they are pretty cheap, at least some of these techniques. Maybe not if you go for a mass spectrometer. Some of them are robust and easy to use. From a thermocouple, you'll always get a reading, right? I mean, you put in a thermocouple and you get a reading which might say 725.5 degrees. The question is how much you rely on that, but that's another question. They mostly give quantitative results, as I said. I mean, you measure. The question is how much you rely on the measurements. Sometimes you get very good quantitative results. Some of these techniques can measure larger molecules. With our techniques that I will come back to later, we have a limitation that we might not distinguish between large molecules. If, for example, many years ago, we looked into the possibility to distinguish between polyaromatic hydrocarbons, phenanthrene, pyrene, and so on. And that seemed to be very hard. Whereas for example, mass spectrometry can measure larger molecules. Disadvantages, well, you have to put in a probe that might disturb the measurement. Also, as I said before, you might always get a result. How do you estimate the errors? It's very hard to measure atoms and radicals, very highly reactive species that are present in the flame. For example, C2 radicals, CN radicals. If you do a conventional probe measurement, they will more or less immediately react and end up in something else. That's why you have to be careful. And then also you have a low or at least unclear temporal and spatial resolution. If you put in a probe, how good is the temporal resolution and what's about the spatial resolution? So that's something that we are working on with lasers. And here is the picture I also showed the other day, where how it could look like when you introduce a probe and you clearly see here that you are disturbing the flame. And then, of course, you influence the result that you get. And it might be very hard to actually compensate or estimate how much are you disturbing the flame. And there has been a lot of investigation, whereas I said before, I don't really have any experience, but this is a very good reference. It's written, it's some years old now by Hayter and Moreira from Portugal, where they investigate thermocouple and sample probes and potential errors that you might have. And there are a lot of different effects that could arise, aerodynamic effects, concentration gradient, thermal effect, catalytic effect, quenching effect. And they go through this pretty much in detail, trying to estimate what the problems might be. So then if we go, that's what I wanted to say about probe techniques. And then if we go into the optical techniques, we have the advantage that it's non-intrusive, at least to a first approximation. I will come back to that. With how high temporal and, at least for the laser technique, spatial resolution. We can, with some of the techniques, measure simultaneously in many points. Some of the techniques are simple. The laser technique is not simple, but the general optical techniques might be simple. In terms of laser techniques, most of them are expensive and complicated. Also the theory might not be that easy. And some of them have difficulties to quantify the data. And I will come back to that. You might not have problems to get a signal, but your signal is the number of photons, and the number of photons has to be correlated to the number of species, which might not be always easy. And also here I will just mention about non-spectroscopical optical techniques that are based on refractive index, laser Doppler, LDV, and PIV. Here, just for your background, also in this case, I haven't really worked with this technique, but there is a very good book written by Felix Weinberg, also pretty old right now, but still very readable on how to use this. Here you sort of have an incoming light, and you have a measurement area, and you can measure what is called shadowgraphy, Schlieren, or interferometry, depending on if you measure the deviation or the angle or the phase. So I set up for Schlieren shadowgraphy, which I know that you have here. You have a light source, you make this light parallel, you put your object, and then you have a detector, and you might have a knife edge. And this is simple and could give, these are just examples from a flame, and you see that you can get a pretty good overview of what is happening. Still with some limitations, of course. You get a qualitative image, but not necessarily and not easily quantitative. And LDV is also, I would say now, a working horse in the field of combustion and flow diagnostics, where you have laser beam, you cross them, and in the crossing point you create a pattern, interference pattern, where you know the distance between the fringes given by this, and then when a particle goes through, you will get a light sort of on your detector, and you can measure the time, and then from the time and the distance you can measure the temperature, the velocity. These are taken from Dantec's homepage, and there are a lot of companies, or several companies, that sell these systems, so they are really commercially available. That's the same with PIV, where you can get 2D images of 2 consecutive pulses. So you put one pulse first to get an image, and then followed by a second pulse, and then you compare these 2 pulses with different correlation techniques, and then you can get a 2D image in the laser sheet of the velocity like this. So in each point you get sort of a direction of the velocity. These are also commercially available. Then we come to the spontaneous emission. You know, if you have a flame, you see the flame, but what do you see? Here is a sooty flame, and what you see is the Planck radiation from the particles. You know what Planck radiation is? I mean, that's essentially all bodies emit according to the Planck radiation. The sun is a good example. And here is given by the Planck's law. Here are shown as a function of wavelength. Here you have the visible region, and if you go for 2000 Kelvin, you see that it's sort of reddish, and then when things is heated more and more, it goes from reddish to yellow to white. This is essentially just because the Planck distribution curve is moved towards shorter wavelengths. So this, of course, as a diagnostic tool, I mean, you see where you have the flame, right? And this can be done with a camera, and then you can get an overview of this. But then if you have a blue flame, this is a conventional Bunsen burner, you recognize this. But if you look at the color, I mean, it's blue. Why is it blue? So in order to investigate that, you have to look at the spectra. And the spectra is the color at different wavelengths, right? So if you have a spectrometer, which is a device where you divide the emission into different colors, you can see that you start with 300, that is in the UV, 400 in dark blue, going into green, yellow, and here you have sort of started to get red. And here you have a lot of peaks. And these peaks come from what is called chemiluminescence, from excited species created in the flame. So you have in the UV OH, and then you have a lot of bands in the visible, mainly from C2 radicals. So the blue that you see here in the flame front comes from C2 radicals that through chemical reactions are creating C2 in the higher states, higher electronic states, and when they lose their energy, they emit radiation according to this. So these are the so-called swan bands, and of course that would give you a very good indication. If you have a flame, you can have a turbulent flame, you can just look for these blue lines, and then you know where in the flame you have the C2, where you have the reaction zone. This is a pretty, yes please.
Why do you have 3 C2s?
That depends on the molecular structure. I will come to this later, but you have electronic state, you have electronic ground state, and you have different, this is the ground states, electronic states, and here you can have emission between, if you have 0, 1, 0, 1, you can have emission where 1 is going from 0 to 1, 1 is going from 1 to 1, and 1 is going from 0 to 1. And you see these arrows have a different length, different, meaning that they have different colors. So this just comes from different vibrational state in the electronic states. I will come.
Be careful with
Yeah. So I will come back to this, but this is sort of here the quantum states has decreased one level. Here it's the same in the both excited and ground state. and here you gain some. So this arrow is longer. And here we come into the molecular spectroscopy. So I will come back to this, but this is, and if you look at this in detail, these are individual lines. So these are, if you have a higher spectral resolution, you'll see a lot of lines. Still, I mean, it's pretty easy molecular spectroscopy to model this. But I mean, just to use it, I mean, you can just put a filter in any of these, taking the strongest, and then you know that you have this reaction zone. The problem, of course, is that this is a line of sight. I mean, when we look at this, we average along this line, right? I mean, we don't know if this point here, this is the flame, and we are looking from this point, right? So what we see is an average of this and that. And if it's a turbulent flame, we don't know exactly where does it come from. We just get an average. So this is a kind of a problem, of course, since you average in the depth of the flame. And it's also very hard, I would say almost impossible, to quantify this. You get a lot of photons, but how to transfer this to number densities? Because these are created by chemical reactions and will give the concentration of the excited state, which not necessarily is what you want to have. You want to have the concentration in the ground state. That's what the modelers want. They don't want to have what is the population up here. So this is pretty simple, pretty straightforward, but still limited in terms of what it can be used for. Then you can continue into the infrared region. Now you have wave numbers, meaning that you are in the visible region. I will define this a little bit later. So here you are in the infrared region, and there you can see that you have a lot of bands from Cu, CO2, water, CO, some hydrocarbons. And here you can see also the bands from individual rotational lines in the molecule. But also in the infrared region, you have a lot of information. That has not been that common to use this since it's a lack of good infrared detectors. But still, you have this information exists. So by looking in the visible and the infrared, you can get a lot of information. Still with the limitation, as I said before. Very briefly about absorption spectroscopy. It's a very simple technique. I mean, you have photons at a certain wavelength coming in, and then you have a medium, and then you have an attenuation in the medium so that the beam that is transmitted has a lower intensity. And that is given by the Beer-Lambert's law, where you have the number of the species, you have the cross-section, the probability for absorption, and you have the length of the species or the transfer of the optical beam. Absorption has been used extensively in combustion, and it's the nice thing is that you get absolute number densities. I mean, you can actually measure n, the number density, and that is what counts for model validation. The problem is that it's a line of sight technique, and that means that you average, especially if you have a turbulent flame, you average over a lot of interval where you might have different temperatures, and then you run into problem. If you make an absorption measurements with different temperatures, you cannot say that you average the temperature, because this is based on the Boltzmann distribution, which define the number of species in different levels, and this is not linear. You can't just take a spectra at 700 or 800 Kelvin and another spectra at 1000 Kelvin, put them together and think that you will have 900 Kelvin. It doesn't work like that. And that is sort of something that I've been discussing with people doing absorption spectroscopy, for example, at Stanford for many, many years. And to my, I would claim that so far it has not been shown that you can use absorption spectroscopy when the species that you're interested in vary in time and space, just because of this. Just look at that. If you would have a turbulent flame and you have the temperature PDF that runs from medium temperature 500-600 Kelvin up to flame temperature 2000 Kelvin, then you have a lot of spectra at different temperatures, and it will be a mess to average this. So that's why absorption spectroscopy is very applicable when you have a constant temperature. Otherwise, I would be a little bit worried. But still, I mean, you get the, in the case of constant temperature, you get the quantitative information, and that is very important. And this is just to show, I've shown taking an engine as an example. You have a laser beam, you have a detector, and then you have beam coming in, you measure, and you get the result on your detector. So this is the setup, pretty simple, with the absorption measurements. Then we come into the main task of this workshop, and that's lasers, and I had these slides the other day also. So here you have a technique which is intrusive, almost intrusive. I will come back to this. And you have high spatial and temporal resolution. We use pulsed lasers, and we focus the beams to very small spots. We have very narrow lasers, high resolution, and we can measure in many points and many species at the same time. And also we can measure when it happens to be non-thermal equilibrium. You know, if you measure in plasma, you might not have a well-defined temperature, because the population on the rotation and vibration levels might be different. So this is important that we can measure really in non-thermal situations. Then, I mean, we have to be honest, right? I mean, this is not just advantages. These techniques, many of them are pretty complicated. Many of them are, I would say, too expensive. To buy a laser costs a lot. And you also have to watch out for safety. I will come back to that a little bit later, but at least these lasers are or could be extremely dangerous for your eye. And I will also say that it's, you need optical access. If you want to measure in an engine just in steel, I mean, then you have problems. Laser doesn't go through steel. Then you have to go to other techniques. And then I said that the lasers are non-intrusive. That to the first approximation. But still, of course, I mean, if you focus too hard, then you can get a breakdown, a spark, because the field strength is so high, so you break the molecules apart, which on the other hand can be used as a technique in itself. Then it's called laser-induced breakdown spectroscopy, and that has been used deliberately to create the plasma. And then you, for example, in steel producing company, or when you want to measure certain metals, mercury or whatever, then you can make this plasma, and then you look for the emission line. You look at the lines, emission lines from this high temperature plasma. And then you can analyze and say that we have sulfur, we have potassium, we have sodium, we have iron or whatever in the spark. So that's a very useful technique for analyzing, for example, metals or atoms. Another potential problem is, of course, if we want to measure atoms. If I want to measure hydrogen atom, carbon atom, nitrogen atom, oxygen atom, I have to be careful not to photodissociate a species. For example, if it happens that I put in so much energy in the laser so that I photodissociate water into water, hydrogen atom and oxygen atom, then how do I know that what I measure does not come from photodissociated species and not the species I want to measure on? So this is something that we have to be careful. On the other hand, once again, this can be used as a new technique. We have worked on deliberately photodissociating species. We were asked whether we could measure hydrogen peroxide, H2O2, which has not been possible to measure spatially resolved. And then we thought maybe if we deliberately photodissociate hydrogen peroxide to OH, it's not that difficult. And then we measure on OH, which we can do very well. And if we know our photochemistry, then we can, by going from the OH signal, go back and say that here is the hydrogen peroxide. And it's in a similar way we can measure methyl radical and other species. So you have to be a little bit careful because when we use lasers, especially in the UV, you can create photochemical effects. And then I would also say up here that disadvantage is, of course, that I wouldn't advise anyone to buy a laser system or LAF system where they claim that you can push the button. These techniques are pretty complicated, and to just adjust the laser, it requires some skill. So I've seen many groups around the world that has been able to buy a laser system, and then they didn't have sufficient support to run it, to adjust it. And even in our group, we can run into problems and have to sort of get the special people from the factories. And of course, this is the disadvantage. There are no turnkey system for this. Okay, this is also something I mentioned the other day. What can we measure? Temperatures. And here we can measure a lot of different temperatures: rotation, vibration, translational, and electron temperatures. Species concentration is based on molecules, radicals, and atoms. Velocities, particle number, densities, diameters, and characteristics of two-phase flows and surfaces. And then, as I said in the beginning, I divide this into incoherent scattering, which is based on linear optics. You have a laser, you send it into a flame, detect as much light as possible, and then analyze the color with a spectrometer and a detector. So once again, if we have our engine as a test example, we have the laser, the detector, and we have the beam hopefully coming out. Now we have optics also. There we have the beam, shaping the beam and measuring through this optical engine. And then we got the image. And there are a lot of techniques like this. Rayleigh scattering, including LDV and PIV. Laser-induced fluorescence, I will come back to that. Laser-induced incandescence for measurement of soot particles. And Raman scattering for major species. And then we have the more advanced, more complicated system based on nonlinear optics, coherent scattering, where we have 2 or more laser beams One of them is what is called a dye laser. It's a tunable laser. We focus them into a common spot where we could have our flame or our engine or our furnace, and then from this crossing point a new beam is generated. So you see the difference. Previously you have to collect as much light as possible. Here the whole signal is generated as a new beam. So that means that we can go 1, 2, 5, 10 meters away and get all of the signal through a small pinhole, which is of course, if we have a very, very luminous environment, an advantage. And once again, if we have the engine where it's set up, the optics, and then we have the beams coming out, crossed in the engine and detected. You see the green and the red beam. This is actually a car setup. Generates a blue beam, goes into a spectrometer, into a multi-channel analyzer, and you get a spectrum. And there are a lot of techniques. I might, as I said, have time to briefly mention about cars. The others have to wait till next time. Good. So that was this. Then we change to okay, so now I don't know how your background in molecular spectroscopy. You might think this is a little bit too much, but I mean, still it's very important that you at least have seen this. And then I'll go into the instrumentation. Just starting with spectral regions. And molecular spectroscopy or atomic spectroscopy, then you work in the ultraviolet, the visible, and the infrared region. And here is the spectra, and if you are in the visible, it's roughly, that's where we see, right, from 400 dark blue up to dark red, roughly between 400 and 700 nanometers. If you are below 400, then you are in the ultraviolet region. And if you are above roughly 700-800, you are in the infrared region. And spectroscopy, if you define that, it says that it's the part of science which uses emission or absorption of radiation to deduce atomic and molecular properties. So by looking at the emission or the absorption, we can take conclusions of the molecular parameters. And here, as I said, we have to go through some basics. All species, atoms and molecules, have different energy level in them. And the energy is defined by E and the Planck constant times the frequency, and the frequency is equal to speed of light divided by the wavelength. So the splitting of the energy levels are directly proportional or inversely proportional to the wavelength. So this is important to know. This is the energy difference, and then you have the Planck constant that is well known. Here you have the frequency, you have the velocity of light, it's very well known, and you have the wavelength. And then we often define if we divide the energy by hc, we get 1 over lambda, and that is expressed in wave numbers. It's called wave numbers, centimeter minus 1. So that's sort of how we in the field express energy. For example, if we have an OH molecule, we have the difference in wave numbers is 35,714. Then we want to convert that to wavelength. Well, I mean, we just follow this formula. 1 over the wavelength is equal to this 35,700 wave numbers. And then if we invert that, we end up with 280 nanometer. And if you remember, 280 nanometer, that's well below 400, is in the ultraviolet. So when I speak of wave numbers, it's always energy, or that you can convert this to wavelength. And of course, there are other ways to convert, to express energy. You can use it in joule or kilohertz or hertz. But when I will speak in the future, it's wave numbers. And then we have to take just some minutes about what is a molecule. And if we have a molecule, it consists of nucleus that are positively charged, and then we have electrons, and they are they keep themselves into a system where they keep together. They repel each other, but the electrons keep, so that the molecule, nitrogen molecule, where you have nitrogen atom and nitrogen atom, it consists, I mean, it's a stable molecule because of this situation. And then you have when the electrons have their lowest possible energy, you say that you have a ground state. That's the ground electronic state. But then you can also have electronic state. I'm sorry. You can excite, you can increase the energy of the electron to a higher level. If you add energy, you end up in a higher electronic state. So now, instead of being in the ground state, we can be in what is called excited states, higher electronic states. So that's how a molecule, to a first approximation, look like. But then it's a little bit more complicated, because the total energy is this, of course. But then you have a fine structure of the molecule. Because of vibration, the atoms vibrate towards each other, and then also rotate. And that gives rise to the substructure that we see in the spectrum. So if we have a molecule, you have the different atoms. Then they vibrate like this, right? I mean, they start to vibrate. And depending on the temperature, they vibrate faster or slower. So that means that we can probe the degree of vibration through the temperature. So that means that the ground state, electronically wise, is subdivided into vibrational levels, both in the ground state and in the excited state. So here is the ground vibrational state, first excited in ground state, and so on. And that's what I wanted to show here, that the emission can go between 0 and 0. But if you go from 0 and 1, then you lose energy, and then you get another wavelength. So all of these bands come at different wavelengths. This is a result of the splitting in vibrational states. And then it's also important to look at